We continue with our discussion of rings. I reiterate, this is the central subject in this class, so we should take the discussion quite seriously. Now, this is about will be about section 3.2 in the book. In this section, there is a further discussion of the definition of rings. There are more notations and more dictionary entries. Much of the previous fragment was sort of dictionary. We introduced rings, rings with identity, commutative rings, integral domains, fields. This is a basic algebraic dictionary and may be taken as such. So we start our discussion of details in the definition of rings with the following. So for in the definition requires the existence of zero. Special element 0 in the ring R, say, such that the element is neutral with respect to addition. A plus 0, same element as A, same element as 0 plus A. For any element A in the ring R. Well, the first question to address is the requirements is that such a zero element exists. There may be several of them. In fact, that's not the case, as the following proposition tells us. In a ring R, an element with this property, as unique. The proof is quite simple. We let 0R and 0 prime R be elements which satisfy the property. This is the requisition, that property. We want to prove that this is the same element, or R is equal to or R prime. So any two elements which satisfy this property coincide. This is the same element. equality means same element of the ring as a set. So we write that OR R prime is equal to OR R plus OR R prime. That is because OR R prime is A0 satisfies that property. For this equality, we took A to be OR R0R. But now 0R also satisfies the same property this way. 0R plus every A is this A. Oh, sorry, 0R prime satisfies the property 0R prime now plus every A is this A. And this is 0R prime plus 0R. So we take this same requisite property with A equals 0 prime. Then this is 0R. So what we see, 0R prime is the same element as the sum. The property with A equals 0R. And this is the same element as 0R. The same requisite property with A equals 0 prime. Thus we find that 0R prime and 0R is the same element. Equality sign in a ring means the two elements coincide. So, property 5 in the definition requires the existence of a solution for equation A plus x equals 0R in the ring R. So again, the question is again the same. We know a solution exists. Is it unique? An argument similar to that we just use for the proposition is presented in the book in the proof of Theorem 3.3. The solution is unique for every A in R. So the solution to this equation is x, is unique. I gave an argument in a different situation. You will read in the book the proof very similar to just given for the proposition for this theorem. This theorem justifies the notation. Negative A. So by definition, we did not have any negative signs before. Now we say definition for an element of a ring negative A is the solution for A plus x equals 0 in the ring. Now we will use the negative sign. Without the theorem, we cannot introduce this notation, because we only know the solution exists. If there are several solutions, we cannot denote the solution by negative A. It could happen that the same label negative A was tagged to several distinct elements. That is a severe abuse of notations and may lead to serious errors. Now, after we know the solution is unique, we may introduce this definition for negative A as a solution. So now we have, of course, that A plus negative A, as negative A is the solution, is 0. And same, negative A plus A, the sum of two elements, is 0. You may put parentheses here if you want. Later on, we'll skip parentheses as we usually do in arithmetic. And this is also a notation for subtraction. What is B minus A? By definition, this is just notation and nothing else. This is B plus the element negative A. Negative A is the solution of this equation. In this way, we've got subtraction in every ring. And this is the way to obtain subtraction. Yet another operation coming from addition. Inverse to addition, of course, the operation of addition was introduced in a way such that we can derive what a subtraction is. In this connection, the operation of multiplication was not introduced in a way such that we can do division. And indeed, in many rings, the division is not possible. You will not divide matrices. You will not divide even integers. There is 3 divided by 2. There is no such integer. This is not an operation on integers, division. Multiplication is 3 multiplied by 2 is another integer 6. Addition was introduced in the definition of rings in a way such that we can define subtraction. And this is the way to define subtraction. Add the unique solution, which is x of equation, and that solution was axiomatized to exist. Next theorem allows for cancellation in a ring. In any ring, A plus B equals A plus C implies B equals to C. This is the same element. A plus B is the same element as A plus C. Then B is the same element as C. The proof is going to be, as usual, You simply add the element negative a to both of them. So this element is the same plus this element plus negative a is the same as this element plus negative a, and a plus negative a is 0 by definition of negative a. Negative a exists and is unique by theorem 3.3, so we can do all that, and 0 plus b or 0 plus c is b or c by the defining property of 0. I will leave details to you to read and in the book, and I want to remark that nothing like that in general is possible for multiplication. Indeed, as an example, in Z mod 6, you have that 9 times 3 is equal, this is 27. In the 6, 27 is the same as 3. 27 minus 3 is 24 divisible by 6. However, you cannot cancel 3 as you cancel a here, but 9 is not equal to 1 in this 6 because the difference 9 minus 1, 8, is not divisible by 6. So cancellation is possible in every ring for addition, not necessarily for multiplication, as this example shows. Some other common sense manipulations are possible in rings, and theorem 3.5 presents a list of common sense manipulations available in the rings. I'll not discuss this whole theorem in these notes, although I will take only one statement as example. I assume you will read the theorem and its proof in the textbook. I will in a moment show you only one theorem out of the list in the statement of theorem with a proof, so that you will see how to read the theorem and its proof. But before doing that, I want to introduce some notations. for a positive integer n, and an element A from the ring, we introduce the power notation n to the n as a up to a n times multiplying a by itself repeatedly n times is abbreviated as a to the n as usual, and it is easy to check that the usual power rules apply. A to the power n plus m is equal to a to the n times a to the m. Whatever a, an element in the ring R, is, and whatever n and m positive integers are. I now want to a little bit enlarge the domain for n here, allowing for 0. You know, a number taken to the power 0 is 1. A ring may have no identity. So there is a big if, and this is a big if, R is a ring with identity, one R identity in R. By convention, a to the 0 or for a different from 0, a to the 0 is one identity in the ring. If a ring is not a ring with identity, that makes little to no sense. We still have this notation, but we don't have this convention. This convention, of course, is compatible with power rule, so everything is all right. Additionally to this notation, we can introduce in a ring with identity zeros powers. Guys, there is nothing about any kind of limits here. It is nothing but convention. There are no continuous functions, nothing like that. A is not a number. It is an element of a ring. That is why algebra is called abstract. This is abstract ring, not necessarily, and most probably not at all, ring of numbers where properties of numbers are available. And this is nothing but convention compatible with power rule. We still can multiply elements. We can abbreviate multiplication as power. That's it. Also, we can abbreviate repetitive additions. So, still, we can, in the same way, write that NA is A plus A plus A n times. And n is a positive integer, we will introduce multiplication by a negative integer as well. Negative n times a as negative a plus negative a n times. Again, by convention, zero a is zero in the ring. We have to be very careful with these things. So A is an element of the ring. 0R is an element of the ring. N, as well as negative n, is an integer, positive or negative integer. So this 0 is an integer. This 0 and this 0 are not the same. They have nothing to do with each other. This is a number 0, and this is a special element in the ring. Different things. At the same time, please have a look. I possibly had to write it this way, negative NA, because this is negative integer and was positive. Negative integer times an element of the ring. But can I also, so I will formulate that as a proposition. Negative n a is the same thing as negative n a. N is a positive integer. A is an element of the ring R, whatever the ring R was. How do we prove that? So the notation is made up so that manipulations are going very smoothly. At the same time, don't forget, this is only made up, and you have to clearly distinguish between integers and elements of a ring. These are completely different beasts, unless the ring is a ring which contains numbers, integers in the first place. But then it becomes even more confusing in a sense. So how do we do that? No, indeed, by definition, negative NA is the unique solution element of R such that negative NA plus NA equals 0. Now, in order to prove the equality, it suffices to show that negative n times a as defined here is equal to, plus, not is equal to, but plus na is 0 in R. Now we look at our notations. We want to show that, let us show that indeed negative n times a is negative a, by definition, this was the definition, negative a plus up to negative a n times and na is defined here as plus a plus dot dot plus a also n times. Now, because since addition is commutative, we can reshuffle them, saying that this is negative a plus a plus negative a plus a plus dot dot plus negative a plus a n times, and every time we have negative a plus a, by our definition of negative a, this is a 0. Negative a is the unique solution of the equation a plus x is 0. So a plus negative a is always 0. So this is 0 in the ring. So this is equal to 0 in the ring plus dot 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 plus 0 in the ring n times again and now by the property of 0, 0 plus something stays untouched, we collapse everything into 0 in the ring A as required. So we showed that negative n times a plus n times a is 0, in this way proving the proposition that indeed this is true. This is not for granted, and we use the property, we use the meaning n is a positive integer, therefore we can do something n times. A is an element of a ring. We cannot do anything a times, no times, nothing. It's abstract. It's just an element of the ring, which may have nothing to do with numbers, especially whole numbers, especially positive numbers. Okay, I will address theorem 3.5 a little bit, just one statement out of the list in the theorem in the next fragment. Thank you for listening.